Hi everyone, I'm Abhika Das, a research scholar student from National Institute of Technology, Silchar, Assam, India. Now I'm going to present my work on green and economical synthesis of glycerol carbonate via microwave-assisted glycerol transesterification over Mangifera indica pill calcine ash, in short MIPCA, as catalyst. Here lies the contents of my presentation. Starting with the abstract. Increase in global population has led to catastrophic depletion of fossil fuels, thereby arising search for a new substitute. Thus, biodiesel, one type of biofuel, serves as an alternative to fossil fuels, reducing carbon dioxide emissions by about 70%. In addition, this massive biodiesel production has resulted in enormous generation of glycerol as byproduct. As per record, 10 gram of glycerol is generated for every 100 gram of biodiesel produced. Thus, researcher focus has shifted to conversion and uses of biodiesel byproduct glycerol into value-added derivatives. Glycerol carbonate is one among such green value-added derivative. In this work, biomass-derived catalyst MIPCA has been researched as heterogeneous basic catalyst in glycerol carbonate synthesis. MIPCA exhibited a high glycerol conversion of 98.1% to glycerol carbonate along with 5 successive reaction cycles of reusability. Our introductory part covers different synthetic routes for glycerol carbonate synthesis, its wide applications, and the advantages of biomass-derived catalyst in glycerol carbonate synthesis. Biodiesel is usually synthesized through transesterification of triglycerides with methanol, yielding fatty acid methyl esters and glycerol as byproduct. Biodiesel byproduct glycerol can be transformed to glycerol carbonate by different synthetic routes such as carboxylation, glycerolysis, oxidative carboxylation, calcination, transesterification. Among all these known synthetic pathways, transesterification is greener and safer appealing approach and hence most widely used. Glycerol carbonate has found wide application in cosmetics, fuel additives, lubricants, lithium batteries, polymeric materials, surfactants. Catalyst plays a crucial role in glycerol transesterification to glycerol carbonate. However, due to easy recovery and reusability, heterogeneous catalysts are gaining popularity compared to homogeneous ones. Different types of heterogeneous catalysts include biowaste-derived catalysts, polymers, nanoparticles, metal oxides, and other supported catalysts. Biomass-derived catalysts have drawn significant attention and wide application in biodiesel and glycerol carbonate synthesis due to remarkable advantages. Catalyst being bio-waste is hence readily available, economical, environmentally benign, and biodegradable in nature. Objective of our work is to synthesize a highly efficient basic heterogeneous green catalyst from biomass and utilize this developed catalyst in biodiesel for byproduct glycerol conversion to glycerol carbonate and reuse this catalyst multiple times without significant loss in catalytic activity. The experimental section, first the preparation of the catalyst. We need to know at what temperature the Mangifera indica pill should be calcined. So, to investigate the desired calcination temperature of catalyst preparation, thermogravimetric analysis (TGA) was performed. The TGA graph shows that no such significant change in mass was observed after 680 degrees Celsius for the fresh Mangifera indica pill. Thus, 700 degrees Celsius was chosen as temperature for calcination. The catalyst Mangifera indica pill calcine ash was prepared by collecting mango pills and grinding into fine powder and then kept for calcination in muffle furnace in a small crucible at 700 degrees Celsius for about 4 hours. The ash obtained is termed as MIPCA. Novelty of our work is that for the first time an effective moderately basic catalyst is synthesized from biomass Mangifera indica for glycerol carbonate synthesis. These catalysts exhibited high conversion with 100% selectivity. We have synthesized glycerol carbonate, transesterified glycerol with dimethyl carbonate using Mangifera indica pale calcine ash derived catalyst under microwave irradiation at temperature of 80 degrees Celsius and time of 15 minutes. Optimized reaction conditions, which I'll discuss in later slide. Microwave irradiation approach encompasses quick and even convection of reaction mixture, which enhances the selectivity and reaction rate to greater extent compared to the conventional method. Glycerol transesterification to glycerol carbonate follows the reaction mechanism where the active basic component of catalyst, here potassium oxide, abstracts the proton of glycerol, generating glycerol oxide anion. This anion then reacts with dimethyl carbonate, forming methyl glycerol carbonate intermediate, which on rearrangement forms final product glycerol carbonate. But a limitation is that in presence of highly basic catalyst, this formed glycerol carbonate decomposes to glycerol by decarboxylation reaction. Thus, synthesis of a moderately basic catalyst is required. So, this MIPCA have been characterized by different analytical techniques. First of all, we shall discuss about the bed analysis. Bed isochron exhibited type 4 hysteresis loop, and the estimated surface area of the catalyst was found to be 3.985 meters square per gram, along with core volume of 0.009 centimeter cube per gram. The BJ's foresight distribution curve, that is the bed graph inset, resulted in pore diameter of 3.127 nanometer, confirming the mass-porous nature of the catalyst. Powder accidity analysis determine the crystalline behavior of MIPCA and reveal the presence of potassium, calcium, magnesium oxides, and carbonates. These oxides are mainly responsible for the significant basicity of MIPCA. Sand and TAM analysis were performed to see the morphology of the catalyst, which revealed collapse of mesoporous surfaces. Selected area electron diffraction imaging confirms the polycrystalline nature of the particles. In addition, EDS analysis showed the presence of several elements, chiefly potassium, calcium, magnesium, oxygen. After calcination, mostly these elements are left behind in oxide form, and this oxides of these elements is responsible for the basic nature of the catalyst. IR spectrum shows the bond vibrations, where which bond stretching and bending vibration corresponds to the presence of moisture in catalyst. Carbon-oxygen bond stretching and binding frequencies correspond to metal carbonates, and lastly, the SiO-Si stretching shows presence of SiO2. X-ray photoelectron spectroscopy XPS gives the elemental composition of MIPCA. We showed the presence of potassium, magnesium, calcium, oxygen, carbon, and phosphorus presence in major amount. This catalyst elemental composition resembles well with the results of EDX analysis. K2P showed two peaks, one at 292.7 electron volt and the other at 296 electron volt, which indicates the presence of potassium carbonate, potassium oxide, respectively. Carbon 1s signal attributed to carbonyl group, which shows peak at 285 electron volt, and the other at 289.2 electron volt is attributed to the carbonate peak. The oxygen 1s spectra was deconvoluted into three peaks, one at 529 by 30.5 electron volt and the other at 531.9 electron volt, which is owing to the metal alumina oxide and metal carbonates present in MIPCA. The calcium 2P spectra gives two components, one at 347 electron volt, which corresponds to calcium carbonate peak for calcium to be 3 by 2, and this 350.7 electron volt. It corresponds to the calcium oxide peak for Ck to be 1/2. Magnesium to the spectra was also observed in the wide scan survey spectra at 51.5 electron volt, which confirms the presence of magnesium oxide. The presence of phosphorus with MIPCA was detected at 133 electron volt, which is due to the presence of phosphorus pentoxide. Let's discuss about optimization of reaction parameters. Firstly, we optimized temperature. It was observed that with increase in temperature, glycerol carbonate yield increased till 80 degrees Celsius, but is decreased beyond that as high temperature might lead to decomposition of glycerol carbonate to glycidol, thereby decreasing its selectivity. Hence, 80 degrees Celsius was chosen as the optimized temperature. On the other hand, while optimizing reaction time, no such significant change in glycerol carbonate yield was observed after 50 minutes. So, 50 minutes was considered as the optimum reaction time. Moreover, with increase in glycerol to DMC molar ratio beyond 1:3, effective collision between the reactant and the catalyst was reduced, thereby decreasing the glycerol carbonate yield. Hence, 1:3 was chosen as the optimized glycerol to DMC molar ratio. Excessive catalyst loading increases the basic sites in the catalyst, thereby reducing the selectivity. As we have already discussed, that excess basic site present in the catalyst leads to glycidal formation, decomposing glycerol carbonate. So, at 6 to 8% catalyst is considered as the optimum catalyst dosage. Synthesized glycerol carbonate was characterized by NMR analysis. This NMR analysis validated the GC formation. Proton NMR analysis showed singlet peak at 2.57 ppm, which corresponds to hydroxyl group. A doublet of triplet was observed at 4.82 ppm, which corresponds to the proton bonded with the tertiary carbon, which is assigned as H2. And a triplet was observed at 4.54 ppm, and a doublet was observed at 4.484 ppm, which corresponds to the CH2 cyclic protons assigned as H1 and H1 dash respectively. A doublet of quartet was observed at 4.01 ppm and the other at 3.74 ppm, which corresponds to the CH2 linear protons assigned as H3 and H3 dash. Glycerol carbonate formation was further reconfirmed by carbon-13 NMR analysis. The most downshielded peak at 156.4 ppm is attributed to the carbon of carbonyl group. Other peak at 76.46 ppm was corresponds to the carbon of CH, which is assigned as C in the glycerol carbonate structure. The other two peaks, 65.7 ppm and at 61.7 ppm, corresponds to the CH2O carbon assigned as C and D. C is the CH2O cyclic proton, and the D is CH2O linear proton. A kinetic research on transacidification of glycerol was carried out at temperature ranging from 35 to 80 degrees Celsius at several time intervals 20 to 20, 30, 40, and 50 minutes. The reaction rate depends upon concentration of both glycerol and dimethyl carbonate. Hence, the reaction is said to follow second-order kinetics. Plot of y versus time gives us a straight line, and rate constant k can be determined from the slope of each line. The Arrhenius equation was used to determine the activation energy, plotting ln k versus T inverse. Activation energy was calculated to be 30.323 kilojoule per mole. Reusability of catalyst is important from both the economic and environmental point of view. So a reusability test of the catalyst was performed by separating and retrieving the catalyst from reaction mixture by centrifugation, followed by washing with methanol and acetone to eradicate any extraneous elements present there. Further, the separated catalyst was dried in an oven for 4 to 5 hours at 80 degrees Celsius. This process was repeated for 4 more steps. The catalyst reusability ensures that MIPCA sustains its catalytic activity for up to 5 consecutive cycles. At the fifth run, the MIPCA exhibited glycerol conversion of 81.5%. Same characterization of reused catalyst after fifth run was carried out to ascertain the morphological changes that occurred in the catalyst. In comparison to fresh catalyst, particles was found to have erratic structures, and EDS spectrum revealed drop in catalytic activity in the active sites of the catalyst. The potassium dropped from 37.72% to 13.5%, and calcium dropped from 9.8% to 4.3% after the fifth run. This loss in catalytic activity could be attributed to the blockage of active sites by glycerol or absorption of water molecules. At last, the conclusion, valorization of biodiesel derived glycerol into glycerol carbonate ensures the long-term viability of biodiesel. Biomass-derived catalyst as a serves an economical and sustainable source for glycerol carbonate production. MIPCA, being biomass-derived and moderately basic heterogeneous catalyst, improves glycerol carbonate synthesis as well as its selectivity. Microwave radiation technique accelerated the reaction rate, reducing catalyst loading and reaction time. MIPCA also proved to be a considerably stable on repeated reuse as a catalyst for up to 5 times. Thank you.